Our next application in the collection of, in this family of 4 algorithms that were the LCS, edit distance, dynamic time warping, and now comes the Frechet. And Frechet asks for 2 polygonal paths, just as before. We have 2 polygonal paths. We are thinking about a dog that can jump from one vertex to the next to the next. We are thinking about a person that can jump from a vertex or to the next to the next. We have to ask, can I move both of them in the Frechet problem? Can I move both of them in the optimal way? And what is an optimal way? In the dynamic time warping optimal way, we'll ask them to be as close to each other so that when I sum up, accumulate the distance between them at each time step, I'm getting the smallest sum of the leash. Frechet doesn't ask about what is the overall sum of the length of the leash, it asks what is the maximum between it. Can I actually do the whole path when the overall length of the leash is, what I want to do use it is to find the smallest less of a length of a leash for which I can find a schedule of the dog, I can find the schedule of the man. Schedule means at which time step which one of them jump. At each time step they have the option of either stay still or jump to the next vertex. In general, they have the option of either jump together or only the dog jumps or only the person jumps, and we want to find the best schedule. Dynamic time warping says if my curves are almost the same, here are my 2 curves, and they are almost the same except of one single point, then when I sum up the overall length of the leash that I need, then it happens only once that I need a long leash. So in the overall summation, it doesn't have a lot of weight. That's about the dynamic time warping. I sum up the total length of the leash. Frechet says, no, if I want to call them close to each other, then they need to be close to each other all along. It's a maximum versus the average, if you wish. Dynamic time warping is not exactly the average length of the leash, but it's much closer to the average length of the leash. Frechet asks what is the maximum distance between them ever. And to find the minimum distance, we are breaking our task. What we really want to find is a mean length of a leash. So I want to find an optimization problem. But to find this optimization problem, and one of the reasons that I'm showing you this example, because it's an example where it's nice to break the problem into 2 separate entities. There are 2 players that are playing here. There is player one that says try leash of 70 meters. And that is player one decide what length of the leash. What length of the leash. And we'll denote the length of the leash as R. R will be the parameter that we'll use to denote the length of the leash. And player 2 will say for this R, can I find a schedule who jumps when, such that their distance, there meaning the distance between the person and the dog, and the distance between the person and the dog when they do this, their little trip along the curve. and player 2 is the one that looks for good schedule, and you ask, can I find a schedule such that the distance is less or equal than R all the time? See what's going? Player 1 is the one that says, I want you to think about a leash of length 70. Player 2 says, okay, I'll try to find a schedule with a leash of length 70. And player 2 answers yes or no. It's player 2's rule to answer yes or no. And once player 2 says yes or no, too short or too long will mean yes, too short will mean no's. I cannot find a schedule, I cannot find the street between them, because no matter which schedule I got, there is some point here and some point here that are just too long with the given length of the leash. You said that I should try 17 meters, 17 meters is not enough. Then player 2 just says yes or no, and then it's the job of player 1 to try again with a leash that is either longer or shorter. So it's binary search on the length of the leashes. Player 2 will decide, hey, if you succeeded with a leash of length 17, succeeded meaning they can walk together with the right time, with more than 17, and we want all work together to find the shortest leash. Then if leash 17 works, maybe you can try a shorter leash. Try now 17 divided by 2. Try 8.5. Yes, yes. If you succeeded with 8.5, then now try the average between, then try an even shorter leash. Maybe 4 meters is enough. If player 2 says no, then player 1 will say, again, binary search like, then try a leash that is a bit longer than the previous one, a bit shorter than the previous one, and so on. Makes sense, right? We just don't know how player 2 works. So, Frechet problem, the algorithm that we are going to decide to discuss, takes a polygonal path P, another polygonal path Q, and this value R, a target length of the leash. Player 1 told him what is the R that you will try. For example, player 1 might say, let's try to get some sanity check. Try the shortest distance between any two vertices, closest you can get. Try really tiny R. Really short leash. Can you find a schedule now? Okay, now with this tiny shorter leash, doesn't work. Try a longer one, and so on. Long discussion. Just in the dynamic time warping, the rules are that either the dog jump or the man jump, or they both jump. And here is a big initialization. I'll still use this array Cij. Guys, video quality, okay? Nobody complains. We still use this array C, just as before. In all the dynamic programming problems, we always have a table that is helping us designing our way. In Dijkstra, for example, this table was just the D value, the estimated value that we give for every vertex. In the case of the LCS, this array C contains two-dimensional array C. I never know what is the correct pronunciation, array or array, I mean the same. In the case of the LCS, this array C contains, every cell contains the distance between some prefix of one string and one prefix of the other string. In the case of the dynamic time warping, we looked at the path. We look at the two polygonal paths, P and Q, similar to the dynamic, to all the algorithms that we saw so far. I will use this array to denote, the rows will denote vertices of P1, P2, P3, P4. P5, for real estate reasons, let's delete. No, P6. I'll use the columns to denote Q1, Q2, Q3, Q4. I'll stick with this example. In the case of the dynamic time warping, we use this array C. The cell 2,2 was looking at the prefix of the first path. Prefix of the path is what? Is a polygonal path that just contains the first few vertices. That's my definition. But the prefix of the path, when I'll write P of 1 dot dot 3, I'll mean the prefix of the first three vertices of P compared to the LCS, compared to the edit distance, compared to dynamic time warping. What is P of 1 dot dot 3? It's the polygonal path that consists of P1, P2, P3. Prefix of three vertices. And similarly, Q11, Q11 dot dot 1, the same notation, is a polygonal path that consists just of the first vertex. It's a prefix of just a single vertex. Q1 dot dot 4 will be a prefix of 4 vertices. And now I'm going to tell you what I'm writing in every cell of the dynamic time warp, of this table C. Dynamic time warping, I used sum of length of leashes. In the Frechet, I just need an answer for player 2. Can you do it with less of length leash? You already decided. The length, right now, your target length is 17 meters. Can you do the whole trip between the dog and the person? Can they walk somehow all together with leash of length 17? Yes or no? And I'll tell you what is CIJ. To know what is CIJ, notation are a bit confusing, but very similar to what we did in the LCS. P of 1 dot dot I is the prefix of the first I vertices of P. Polygonal path of the first I vertices of P. P11 is just a single vertex. P15 will be the whole of the path. P is the blue path over there. Q1J, the same thing. R 17 meters, the same 17 meters that we saw earlier. Frechet is a Boolean function, it's a Boolean method. It tells you true or false, yes or no. CIJ should contain yes or no, depending on whether the Frechet distance, but not between the whole of P and the whole of Q. You do the whole trip between the whole of P and the whole of Q, but just between some prefix of P and some prefix of Q. quick example. Here is my leash. The length of the leash is this distance. This point and this point. I'm trying to say that's the Euclidean distance between them. What do you think in the example on the whiteboard? What should C11 contain? C11. What I wrote in this cell. Okay. What is written here? I tell you first. Compute what is a prefix.
Distance between P1 and Q1.
Yeah, let's go slowly. First, it tells you look at the one. This one over here is C11. The I over here tells you look at the prefix, the polygonal path that contains vertices from P1 all the way to P1, which means just P1. So the prefix of P is only P1. It's a polygonal path that contains a single pair vertex. What about Q1? Q1 dot dot 1, J equal 1, just one vertex, Q. Let's look at the Frechet between P11 and Q11 with R. R here is, what do you think it is? I think that it's about 12 centimeters. Let's say that that's 12 centimeters, what I do here. What do you think P11 should be? Remember, in C I don't write the distance. In C I just write, can I do the whole walking, the whole schedule domain where I use only this leash? I don't never need a longer leash. Maybe they'll be closer than this length of the leash, but the person dog will never be longer than this length of this leash.
If the distance between P1 and Q1 is less than or equal to the length of the leash, so we write true or false.
Does it look to you by eye that the distance between P1 and Q1 is length at 12 centimeters, right here?
Yeah,
To me, it looks like this is longer than this.
yeah.
This is about a marker and a bit. Maybe I want to make it slightly longer. Now, I'm kind of sure. Now it's almost 2 markers, long enough. Look at the distance between P1 and Q1. Good enough, right? Less than. That is, if the only goal of the man and the dog is not to walk all the way to the end, but just to stop at P1 and Q1, that's a final destination. It's a starting destination, but also the final one. Then the length of this leash will do. Everybody agrees? They can stand over there, and the person can stand here, the dog can be here. The dog can be here, the person will be here, and the person will hold the dog with a leash of 12 centimeters, and that's fine for this trip, the trip at which they end or at CI, they end at PI and QJ in this case. They end, since I asked for PC11, I mean, I can do this trip when they're standing right here because the distance between P1 and Q1 right here is less than 12 centimeters. So what should I write in C11?
Yes.
There is, yes. The bullet. Yes, they can stand there and they are not, the person can hold the dog by the leash. The distance between them is not more than the target length of the leash. R right here, this length, this leash is R, and we are checking this length of an R. Yes, on Zoom, make sense? let's check it. C11 during the initialization step. How did we initialize LCS, LED, standard dynamic time looping? We first filled all the cells at the leftmost column. We filled all the cells at the top row, and then we did a raster scan for I go from 1 to n, for J goes from 1 to n, filled out all the rest of the cells. That's exactly what we are doing now. So C11 in particular is 1 in this case. And how do I know the initialization, what is C11? I'm checking if the distance between P1 and Q1 is smaller or equal than R. Remember, it's a Boolean value. The distance between P1 and Q1 smaller than R, it's a Boolean value. It's either yes or no. What's the rationale here? If I want to ask altogether if I can do the whole trip with a leash, or say, my next step, if I'll get the answer that 12 centimeter is good, then in my next attempt, maybe I'll try a leash of 6 centimeters. So with a leash of 6 centimeters, with a leash of 6 centimeters, I ask, can the person on the rope roll all the way using a leash of 6 centimeters? But they always start at P1 and Q1. If even when the person is on its first vertex, the dog is on its first vertex, and the distance is already larger than 6 centimeters, then there is no point of asking for other cells. Definitely you cannot do the whole trip if even at the starting point the distance is already larger than R. Okay, so the answer right now will be yes. Before we continue with the code, just to see that everybody is still breathing, let's try this leash. I'll say that is 30 centimeters. So in particular, if you see this distance is larger, this distance is larger than the distance between any point of P and any point of Q. Can you tell me what the table will look like when I'm done? For this particular leash, it's very long leash with respect to P and Q. What will the table look like when I'm done? For this instance, really, really long leash.
All of it will be yes.
Everything will be yes. All the cells will be true, will be yes. Because no matter how they are progressing, they are never, I picked really long leash, no matter how they are progressing, no matter what the schedule, there are not 2 points that are more than 30 centimeters. So in this case, it will be yes all over the place. All the cells will be yes. Guys, part of the being with a mask, that is, encourage, of course, to be with a mask, but it's hard to read if it's understood or not. So if something is unclear, please be vocal. Okay, we continue with the init step. Now I want to fill the leftmost column and the top row. For I goes from 2 to n, I want to know what is Ci, comma 1. Let's understand what is C of I, comma 1. What is a 1 set here? That I'm looking at only at path, polygonal path, which is prefix of the whole P, but I'm only looking at trips at which the person starts at P1, he always starts at P1, but never leaves P1. The person is glued to P1, cannot leave this vertex. What's the I over there in this case? What is this I over there tells you? the I over there tells you that the dog is the one that is allowed to move further and further on its curve. So can you tell me in which condition will I write yes, or it's P, so it's P1, I'm sorry, I mean P, C1I. When will I'll write yes for the whole first row? What condition will be if I can write yes for the whole first row? The person is glued to P1, and the dog can move forward all the way up to Q4, and all these distances from P1 to Q1 P1 to Q1, P1 to Q2, P1 to Q3, P1 to Q4, all these leashes are less than R, less than your target. Then you'll write yes all over the place. Good. So in particular, Cij is what? What are the conditions that will guarantee it? It should be that Ci1 should be if the dog, it consists of two conditions. It's a Boolean and right here. First, it means that C, if I look at, let's think about C1, 3. The person is glued to P1. The dog is at Q3. Hopefully the resolution is large enough in at least one of the cameras. If not, then please yell. Even worse. And probably for the future, I need to okay. I'm looking at C13. The person is glued to P1. The dog is at Q3. And what does C13 should stand? Whether the person can stand here and the dog will continue all the way from Q1, Q2, Q2, Q3, and be at no more than distance R, leash of distance R, will do. So in particular, a necessary but not sufficient condition is that the distance from P1 to Q3 will be yes. It is the distance between P1 to if the distance between Q1, I made a side, that the dog that is stick, I'm sorry, I got it wrong. Well, the dog that is stick to Q1, and I'm looking at P31. I'm looking at C31. What's a condition that they can be there? The dog is stuck to, the dog is stuck to Q1. The person is at vertex 3. The distance between them should be less than R. And in addition, this distance and this distance are also smaller than R. Remember, I'm trying to fill out what is C of I, 1. I, 1 meaning dog stuck at Q1. the man is moving along the other vertices. So how can I write it efficiently? Is the distance from Q1 to Pi. If you didn't understand it by now, when I write Pi minus Qj, Pi and J are points, and Pi minus Qj is a vector. When you put the bars over here, it says that's the length of the vector, that's the distance, Euclidean distance. So is the distance between Q1 and Pi is less than R. And in addition, C of I minus 1, 1, that I just computed in this loop is 2. This is a true value. So this is just a shortcut. When I write C13 is true, it's just a shortcut then. P1 minus Q1, P2 minus Q1, and P3 minus Q1, this, and this, and this, these are all two. And this is smaller than R, this is smaller than R, and this is smaller than R. All three are two. This is just a compact way to write it down. So that takes care of the initialization. And the next line is just the same. This line is just the same. Takes care of the filling up the first row. I'm not going to in general that it will all be yes, of course. But notice that if I have, no over here, then it will mean that I also have no over here, also means that I have no over here. Because it means you cannot have the person stuck here and the dog continue to do all the way and using only a leash of length R. And once again, R is some number that you decided about, the first player told you about 17 centimeters, that's what you're trying. I gave you a long, long, long speech about the whole algorithm. Let's see what's the code of this algorithm. Very typical to dynamic programming. The code of the algorithm is so simple. The init was on the previous slide. For I goes from 2 to n, for j goes from 2 to n. Cij is, what should be the condition? What should be sufficient for me to write that Cij is, true, is yes. In this example, I am looking at a black marker somewhere. In this example, to write that if I want to write that C5, 4 is yes. Maybe. That's what I want to write. What should happen? What would guarantee it? Or what will be sufficient to say it's no? It asks, is there any way that the dog and the man can move? And I'll remind you the move meaning at every time step, either dog move, or the man move, or they both move. And always one vertex to the future. I'm looking at P5, I'm looking at Q4. Right now, this is the length of my leash. What was it? Let's say 20 centimeter. This length of the leash. I'm asking is the distance, since they must end at PIQJ. We're talking about the whole Frechet of the prefixes. In particular, now I'm looking at the whole prefix of P, which is whole of P. the whole prefix of Q, which is whole of Q, and they must end at P5 and Q4. When the person is at P5, the dog is at Q4. Maybe there are other times that the person is at P5, but definitely in the last step. That's where they end their trip. So I first check the distance between P5 and Q4. Right? Check the distance between P5 minus Q4, the distance between these 2 points, and check if this is less than R. And if the answer is no, these two vertices are already too far away. The distance between P5 and Q4 are so far away. Let's write a different example. Here is P, different example. Here is Q, the different example. P1, P2, P3, Q1, Q2, Q3. And if the distance between P3 and Q3, the final destination is more than the length of the leash, then the answer in Cij should be definitely no. You cannot do the whole trip because you cannot even finish it at this point. Right? So the first condition that I write in Cij is that I'm asking is Pi minus Qj is smaller than R. If the answer between Pi minus Qj is larger than R, then Cij must be false. But that's just a necessary condition. It's not sufficient. If the distance is less than R, then it still doesn't mean that Cij is yes. Agree? Let's think about this example. This is P, this is Q, this is P, this is Q. My target length of the leash will be still this green thing. Is the distance between P1 and Q1 less than this length of the leash? Yes. So we start good. Is the distance between the endpoints is less than R? Yes, we end good. So we pass these two conditions, but it still doesn't mean that I can find a schedule for the whole trip, that it's always smaller than R. I need to find a schedule where all the time they are smaller than R. So my first check is Pi minus Qj is smaller than R. And even if no, then I'll write Cij is no, false. If the answer is yes, then as you know from C and Java, when you have a Boolean condition, you don't even check the false. Once you have a false, you don't even check the next condition. But even if you have a positive answer, then you're moving to check the next condition. So what is the next condition? So in my case, here I'm in this P5, Q4, and I'm saying I check the distance at the endpoints, and yes, this distance is less than 20 centimeters. What I'm trying to decide right now is P5, Q4 is what do I write on this cell? What do I write on this cell? I pass the first condition, this distance is less than R. What happens one time step ago? At every time step, either the dog jumps, or the man jumps, or both jumps. Where were they one step ago? Three options. Possibly one time step ago, the person was at P5 minus 1, P4, and the dog was at Q4 minus 1, Q3. And how did they do the last step? Both of them jump. That's one option of what happened in the last step. Another option was the person was already at P5 and the dog jumps from Q3 to Q4. Right? So that will be the case that the person was in the previous step at P5, the dog was at Q3, and then the dog jumps from Q4 to Q3. Previous step was P3 and Q3 was connected, and the last option, only three options, last option was that the one step ago, before the P5 to Q4, one step ago, the dog was already at Q4, while the person was at Q3. So if we're making okay, we have a technical problem because the clip is broken. So we'll improvise something. Sorry for the noise in the recording, the clip just broke. So what's the rule of the condition? When can I say that this is yes? Well, I pass the first condition of what happens at this distance. Hello, hello. You want to help us TAing? Pete, you was my TA for this course several summers ago. Congratulations, by the way. He's very, very fresh doctor. So one step ago, one of them was previous, and what was the necessary condition that I can do the whole schedule? I must go do the whole schedule with a leash of 20 centimeters, subject to one of the three steps I can do with a leash of 30 centimeters. Either the dog and the person are at P3, Q3, or it's P4, Q3, or the, what did I write P3? P4, either they are at P4, Q3, or they are at P4 and Q4, the dog arrived earlier and then the man jumps, or the person was at Q5 and the dog was at Q4. And how do I know if I can do the whole trip to this location with this length of the leash? I don't need to solve the problems recursively. I can call the function Frechet recursively, but as we saw, it will lead to this terrible recursive call of multiple things. We are using the principle of memorization. When I want to know what is Cij, I don't, it's one answer that will not change how did I get to this position. It's just one answer, correct or incorrect, needs to be computed just once. If you don't understand what I'm speaking about, go back to the first class about the LCS. So I'm using the idea of memorization. When can I say yes? If this distance between the last two vertices is yes, and either this cell is yes, one of the cells that I will write here. Either this is yes, or this is yes, or this is yes. At least one of them must be yes. Because it means there is a way to reach all the way to here. There is a schedule of the dog and the man that will take you all the way to either here or here or here, maybe both. And all this time you don't need a longer leash. So I'm checking what is the value of Ci minus 1, J minus 1, which means they both jump in the same step. But if Ci1 minus 1, J minus 1 is 2, it means you can have them walk all the way to Pi minus 1, Qi minus 1, and then both jump at the last step. And you can do the whole step. The yes here means yes. leash of length 20 will fit to this type of trip. This, if Ci minus 1j contains yes, it means the person jumped from Pi minus 1 to Pi, and the dog stays at Qj. And this is just a symmetric case. So this should contain true, or this should contain true, or Boolean, or this should contain true. And it's not XOR. If two of them are fine, that's good. But that's the only case that you'll write yes over here. Okay, and that summarizes the Frechet. What do I tell the user then? What is CNN? What is written at this cell? Can you do the whole trip with a leash of length R or not? But the running time, not much to discuss over here or optimize, n squared. Number of vertices of P times number of vertices of Q. What is a space requirement? As usual, if I want to store the whole table, then it's n squared size. But if I just want to know is the answer to the Frechet is yes or no, then I can do our choreography of write from one array, or read from one array, write to the other array. When you're writing into the last row, you only need the row before that. Okay. The answer, I'll be right back. Let's do a quick example. Do a very quick example. So that would be P1, P2, P3, P4, P4, the same P4 and P5. P5, this row is P5, sorry. And just quick sanity check. I don't need the last row. That would be actually P4. And my target length of the leash in this example is this length of the leash. really this flex of a leash. Okay, let's fill the table with these two curves. Very, very simple example, very synthetic example. Let's go to the initialization. This is your length of the leash. P1 minus Q1 is more or less than this distance. Over here, by eye it looks at yes. So C11, the answer between P1 and Q1 is less than this leash. So I'll write yes over here. I'm still in the initialization. P1 minus Q2, this distance versus this leash. By eye looks like no. Definitely not this one minus this one, definitely not this one minus this one. So this is yes, and similarly no, no, no. When we are checking the distance from Q1 to P1, P2, to P2, P3, P4, too long with respect to this leash. So that's what the table looks like after the initialization. And for I goes from 2 to n, what's going to happen? What do I write in C22? C22 I'm asking, let's check, C22, to know what I'm writing in this cell. What am I checking? First, I'm checking the distance between P2 and Q2. Comparing to this distance, if I draw it correctly, this distance is smaller than this length of the leash. So this condition is checked. Now, what about the next condition? There are two conditions that should happen. What about the next condition? True or false? People in Piazza, you're more than, people on Zoom, more than happy to. I'm checking the second condition. P2 minus Q2 is less than R on my drawing, and I'm checking next the next condition. And let's look at the following three conditions. What are you saying? I need to check, from this cell I need to check the cell to my left, the cell above me, the cell diagonally for me, and the cell above me, and to ask, is any of them contained yes? And the answer is yes, this cell is yes. This no, no, yes, which means, and the distance between P2 and Q2 is less than R, so I'll write yes. What do I write here? P2, Q3. P2, Q3, this length of the leash, this is about marker without giving. Well, P1 minus Q3, this distance, P1 minus P2 and Q3, more than the marker, too long. So this condition already failed. So this will be a no, no, a Q3 and a Q2 and P3. It's hard to see, but this is Q2 and P3, Q2, P3, too far away. No, what do I write here? P3, Q3. The distance between them is yes, and one of the surrounding cells, namely diagonally, is also yes, so this will be yes. No, 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 and this will be yes as well. And notice that if now I can track how come there is a yes here, who gave this cell the value of yes, which one of its neighbors. Here it's easy because there is only one. I'll go to this cell, going my way backward from the bottom right to the top left. Paving the way backward. From this yes, who gave this one? This yes will mean there is a time that they're standing here. These 2 points match each other. There is a correlation between these 2 points. If I drove along these 2 trajectories, probably that's the same point on the 2 trajectories. That's GPS location. Who gave me yes in this case? These 2 guys. Now go tracking myself backward. Who gave this yes over here? This guy. Tracking it. This will be a matching between these 2 points. And similarly, going myself 1 step backward all the way to the top left corner, this will be yes. So this is the correspondence, the alignment between these 2 curves. And we are done with Frechet. In general, of course, it doesn't have to be one-to-one. We saw this example. It could be that here is P, common example. Here is Q, this is P, this is Q, and the only alignments that I might get will be this one. About all these vertices over here matches this vertex, meaning that the dog was staying still while the man moved forward. Then they'll jump to the forward one. These 2, all these points match each other, and so on. Okay. Next example. Few comments. What we discuss is a discrete Frechet because we only measure distances between the endpoints of the 2 curves. Continuous Frechet meaning that they are moving continuously along the curve. Every point counts. There is less importance about the part. Now you can speak about the weak Frechet versus a strong Frechet. Weak Frechet will ask, can the dog move, or the person move backward or not? And I'll ask you in the homeworks to play with similar questions, weak versus strong. And also look at this table. It's a hint to some other homework question. Look at this table. You can think about this table as a graph, where every cell over here is a node, and it's connected to, or not connected to its neighbors, and possible, what am I looking in this graph? I'm looking in some sense, in the Frechet case, I'll call this cell source, I will call this source destination, and I'm looking for a path in this graph from each cell to neighboring cells that only going through a yes cells. You can play with such thoughts to both think about the Frechet as well as think about this graph, and now add some weights to the edges, and now this weight of edges corresponds to sum of length of leashes. That's a dynamic time of it. And you can come up with many other algorithms as well. There are lots and lots of variants of the Frechet. So what did we take from dynamic programming thing? Hallmark. So far, we see that optimal solution to some problem contains optimal solution to one of the sub-problems. The optimal schedule to go to P4Q4, the optimal schedule to go to P4Q4 contains in it the optimal schedule to just go to P3Q3. From the beginning only to P3Q3. Or the optimal solution to go to P3Q4 or one of these other sub-problems that we need to check. We don't know which sub-problem exactly. Again, the analogies that I'm going to like to bring, when I'm finding the shortest path from S to T, I'm checking what is the shortest path from S to V17. Why? I'm not sure that I'm I need the distance to from S to T, not the distance of V17, but in case that I'll go via V17, this is the shortest path that I will use. If the shortest path from S to T uses V17, it definitely uses this path. So that's the example that we saw in the case of the LCS. Every perfect of the optimal solution is a solution to some LCS problem for some prefix of X and some problem of Y. And another rule is that how many sub-problems am I solving? There is not too many sub-problems that I need to solve. I'm sure I don't know that, just looking at this example, I don't know that there will be ever a state that the man is at P3 and the dog is at Q3. However, when the man is at P3, the dog must be somewhere, and I'm just checking all these options. I'm just looking at all the sub-problems that are defined by look at some prefix of P, look at some prefix of Q, because one of these prefixes is a corrector. This final solution is a corrector. There is no other way that when the person is at PI, the dogs must be somewhere, and we are just checking all these cases. You'll have to solve lots of other problems before you feel really convenient with it. Okay, we are moving towards our last dynamic programming example. Try to increase it a bit. Okay, this is a problem that I took from Kleinberg and Tardosh book. You can get it in the library. You can go. I can Xerox for you a few pages from this book if you're losing me. It's one of the books that I recommended for this course. But this example in particular doesn't appear in the CLRS. Okay. So I want to look at the data to first a big picture. What is the input to my problem? The input to my problem is a set of points, xi, yi, and they are ordered. They are like data points. Here is P1, that is x1, y1, P2, P3, P4, P5, P6, P7, P8, P9, and so this will be P10, and this will be, I think, P17 somewhere with all these points. And I'm asking you, hey, look at these data points. Look at the x-axis as a date, and PI is how much our company was. And can you specify some trends in the data? All these data points tells you about something that happens in the market. Can you tell me that there is some period that it behaves like this, some period that it behaves like this? Can you partition it into something bad happens, something good happens? And you're looking at this data that I carefully drawn over here, and you're saying, yes, this is P1, P2, P3, P4. It looks like our value was nicely going up constantly until at some point, somewhere, there should be some bad thing happens, the value of our company starts declining. It's then we are on the uphill again for the rest of the points, and so on. But something that is a bit hard to say based on individual points, especially if each individual point has some noise in it. I cannot say about this individual point it's necessarily higher or lower than its neighbors. There is some noise into it. I assume that these lines that I just drew never stab the data points exactly. They're going near the data points. And I want to understand what does the data tells me. What are the main clusters in time that happens? Can I say here is a group of points? Here is one group or one cluster where things was going up, so this will be cluster 1. I'll think about this point as cluster 2. And I'll think about this point as cluster. And it's up to us to think about what are these clusters, if there are any. Maybe I cannot say anything meaningful and it's all in one cluster. Maybe there are a lot of clusters. Can I make sense, do some data science over all these data points? So I need to cluster them. And the problem of clustering is maybe one of the fundamental problems of machine learning. You've heard about it undoubtedly many times, on many types of clusterings. And usually clustering is NP-hard. And if you don't know what is NP-hard, our definition of NP-hard problem in this course are problems that you can write an algorithm for, but you will not live long enough to see this algorithm terminates and give you any result. That will be our definition of NP-hard. Well, it's tongue-in-cheek, but problems that, as much as we know, there is no polynomial time algorithms that will solve them. So clustering in general is very hard, especially if my points live in higher dimension. But here my points are all living 2 dimensions. And there is a clear time that helps me to cluster. I want to cluster the points based on the x-axis, based on time. So the x-axis is a time also. And to ask what do I mean by cluster, I want to say a cluster is a period where my points more or less fits one line. My points more or less fits one line. I'll be much more formal than this. And to answer this question, I first want to ask, if I just want to fit a single line, all my points live in one cluster, I want to fit one line into this point. How do I do it? There are many ways to fit a line to a set of points, but let's use linear regression. Linear regression says the following. Look at x1, y1, and let's assume that this is a line that I have in mind. This is my line, and I'll write this line as y equal ax plus b. This is not necessarily part of the material, you just need to know that there is such a formula. But it's a good way to measure it. So let's assume that this is the line that I'm trying to fit to my point. I'm looking at x1, y1, and ask what is the vertical distance between this point and the line. The vertical distance. Here is my line L, y equals ax plus b. Here is my point x1, y1, and I'm measuring this vertical distance. And of course, I can change this line so it goes exactly through this point, but there is a bunch of points that are in the game. There is also, I measure this vertical distance between x2, this distance with respect to x2. Another point over here, and another distance. Yada yada, and I'm done doing it for all the points all the way to x and yn. And I want to find a line that would minimize the error. How do I define the error? I can look at this distance plus this distance plus this distance plus this distance just to sum up these distances. But this expression is not nice. It's not differentiable. It means that if my line suddenly jumps from above the points to below the points, then I have a point that I cannot differentiate. It also has issues that if I just sum up the points, and if there is only single line that is far away from the line, but many of the points are close to the line, then I still think that it's a good fit. So I sum up these distances. That's what I want to do. But I'll say for various reasons, instead of sum up the distances, I'll sum up the squares of this distance. So this expression, what is yi minus axi minus b? Let's look at this point x1, y1. What is a green point over here? If my line is ax plus b, then this green point would be ax1 plus b. This is y1 prime, this value over here. What is the distance between y1 to, I'm looking at y1 minus y1 prime. y1 prime is a point just below my data points on the line itself. Look at this distance. Take the square of this value. This gives you the penalty. It means that far away points get much more weight. Sum up this number, and now find the line that minimizes this number. Find the line that minimizes this number, and if you all know how to compute the differential, to compute the derivative, it's very easy. You take the derivative. Since you are trying to find the line, it means find A and find B. If you don't know, and that's fine. You're in your last semester. You don't need to study it right now. If you do know what is differential, then you're saying, let's take this expression, takes the derivative by A, making equal to 0, takes the derivative by B, making equal to 0, solve these two equations, and here is a formula that tells you what is the optimum A that you are taking, what is the optimum B that you are taking. This is a formula that tells you what is the best line that you need for one set of points. Guys, to the three of you, sounds familiar? So linear regression before that at some point. If not, it's not crucial. Just remember, once I have this set of points, then it's easy and in actually linear time, I can compute A, what is the optimal line, and B, what is the error that this line gives with respect to this set of points. What is the error? What is the error? The sum of the error with respect to x1, this distance squared plus the distance. This distance squared plus this distance squared plus this distance squared. If I'll use this value of A, this value of B, then this error will be as small as possible with this set of points. In particular, if the points are collinear, then obviously this line will just go through all these points. If my points are something like this, then maybe my line will go somewhere in the middle between these cluster of points. Anyhow, all I need for the remaining of the algorithm is that there is such a formula, and you can compute it in linear time. That's not the problem that I want to solve. People solved it long time ago. The problem that I do want to solve, and we'll continue next week, is the following. I gave you a set of points, P1, P2, all the way up to P12 in this case. I gave you these data points out there. And just as what we had on the whiteboard before, I want to cluster them. Usually, when I gave you all these points, I don't have this color. I added this color just to understand what are these clusterings that I'm looking for. But it's clustering in time. I'm trying to break the time into periods. Here, from January to February, the market was fantastic. It went up. From February to March, the market was crashing, and so on. I want to ask, what is a meaningful cluster that you can find? But this question usually, every time that you are asking for clustering, the people that you're talking to clustering about will come up with the question, how many clusters do you want? You cannot ask me how to cluster my data without telling me how many clusters I want, because let's look at this data. Here are my points. For font, I'll just call them 1, 2, 3, 4, 5, 6, 7, 8. Can I find a line that fits very well points 1 and 2? Absolutely yes. You can actually find a line that goes through them with zero error. I can also cluster 3 and 4, 5 and 6, 7 and 8. There is zero error over here, but there is a lot of clusters. Like every 2 points have a cluster. I can also decide that all my points must be in one cluster, and then the error will be larger. The error means the sum of squares of the vertical distance. So how do I know how many clusters do I want? Well, in this problem, I'll tell you the user will have a tune-up parameter, will have a volume rules that will allow the user to control the number of clusters. But control the number of clusters, I'll tell the user something smarter. You know what, you don't want really to guess the number of clusters ahead of time. Instead, think about this as a process for which every new cluster has a penalty. Every time that you are starting about a cluster, you need to pay a penalty of $5 plus the errors that you are getting. $5 per each cluster. This $5, $5, $5, $5. So here I have error, zero error, as far as my lines fit the clusters very well, but since I have a lot of clusters, I need to pay $20. What happens if I find only one line? Then my error will be much larger, because now my error is something like the squares of all these red lines, but I only need to pay a penalty for one cluster. Make sense? And then I'll tell the user what you are paying in general is $5 per some penalty per each cluster. We'll call this penalty R. One penalty per each cluster that you use, plus the error that you're getting between the best line that fits this cluster. Again, what the user needs to pay once the user decides about the cluster is R dollars per each cluster, plus the errors that you are getting between the best line for this cluster, called L1 here, and all the points in this cluster. There are a lot of new ideas here, and I know that it takes time until they digest. But I explained this problem for many generations before you, and it always worked fine at the end, but give it a bit time. So what do we mean here? The user will start to say, my penalty R is 0. It costs me very little to pay for a cluster, and if it costs me very little, then I can afford a lot of clusters, and then I'll pay very little for an error. And then the user will have this tune-up parameter, volume number that he uses, and the user will increase R to be a larger and larger value. And as you're changing the penalty, when R becomes, instead of $5, $500, then you'll say, definitely for $500, lots of money, I'll use only one cluster. If I decrease the R, then it will be fewer clusters. Notice why I'm doing all this strange gymnastics. There is no correct answer to how many clusters I need. There is no correct answer to how many clusters they need. The user needs to look at what is a matching, what is a clustering that I gave the user for this number of clusters, this penalty, and says, I like it or I don't like it. There is no correct value of the penalty for R. It's something that the user needs to decide or play with, but for every value of R, the problem is well defined. It's a nice optimization problem. The user told you, for I want to try R that is $17. Now, for this particular penalty for what? Every cluster you have to pay $17, plus you have to try to match the points to the clustering, and mind you, you still don't know what are the clustering. You still don't know how to break the points. But for this particular set of clustering, how many clusters, what is the best partition that I'll get? It depends on the data. It depends on how well you can fit the points, and it depends on the data, of course, and it depends on what the value of R. And the user can play with different values of R. So let's state the problem. Let's state the problem and send you home, and don't expect that it will be completely clear on our first side. So our input is a set of points P1 Pn. Again, think about the x. Each point is in 2 dimensions, and think about the x-axis as a time. When I'm telling about a cluster, when I think about a cluster, I'll always think about a contiguous set of points. My cluster will never contains P1, P7, that will be a cluster, but does not contain P6. If you're saying that P1 and P7 are in the same cluster, then P2, P3, P4 must be, or P6 must be in the same cluster. Once you told me where the cluster starts and ends, at which period, think about it as a period of time. Period of time is a cluster, or the point in this period of time, this x value, must be in the same cluster. So it's just a question of where do I start a period, where do I end a period. So sorry for the double indexing. Let's try to make it a bit larger, and then I'll send you home. 2 more minutes. And so, input to the problem. The input are all the points and some penalties that the user decides about. What is R? $5 per cluster. What I want to find is K. K is the number of clusters. And mostly what I want to find is a partition of the number of points into the word cluster is less well defined. I'll call it, instead of clusters, I'll use the word run of points. A run of points means I'll take the points at, say, P6, if you can see, and I'll end this point at P8 over here. And P6, P7, P8 is one run. It's one cluster, but I want to say I cannot drop points from this one. From the set of points, all the data points, all your stock between January and February, you need to decide when you start a run, when you end the run, but you have to use all the points between the beginning of the run and the end of the run. So I want you to tell me that an optimal clustering will start at P1, always the first point, and will end at a number that the algorithm needs to find, which we'll call I1. I'll prepare this slide better to the next week. Pi1, P5 in this case, and what is the penalty that I'm using just for this one, for this cluster? First, I'm paying R because it's a cluster, and B, I will take the points from P1 till P5, compute the best line, compute the error that I get for this line. Is this line really fit the points very well? Is this line far away from this point? Because I still don't know that this is a good one. And the penalty that I pay for this one will be R plus this error between the optimal line and this point. But I have to pay for other clusters. If my run end at P5, then the next point will be P6. That's where a new run starts. And I need to decide for P6 who will be the other points at the same run, at the same cluster. And what do I take? Find the best line that fits this point, L2. Find the run with these points. You're paying how well the line fits the points, what is the sum of distances, plus you're paying up. And so on for the third hour, so on for the fourth, fifth, seventh. How many hours? You will tell me how many clusters. Where do each run start and stop? You will tell me. But you'll do it in a way that the overall cost that is written here will be as small as possible. Take my word, it's much harder to understand what exactly I'm trying to solve here than how the algorithm works. It will be a long explanation about what the algorithm that I'm going to solve, instead, what the problem that I'm going to solve, instead, how do I actually solve it. So, once again, 30 more seconds. One, two, three, 4, 5, 6, 7, 8, 9, 10. And I'm asking you, what are good periods here? How should the points, and let's add a few more points. Okay, lots of points. Where do periods start and stop? And probably the answer that you need to tell me is that if you pick R as 0, pick R as 0, very small penalty, again, the user decides what is R, then what will be the clustering that you'll get, what will be the run. Take point 1 and point 2 together, put a line through them. Take 3 and 4 together, put a line through them. You don't pay any error over here. And you can afford tons of runs because you don't pay any penalty for each one. Take R to be $5,000. Since it cost me so much, R is how much each cluster cost. R is $5,000, a lot of money. I will be afford only one line. It will go somewhere here, all the way from here to here, and the error will be the error between this line to all these points. What do I expect the algorithm to do, if it's reasonable, is to say your first one starts at point 1 and ends at P3, and here is a line that best fit these points. Your next one starts, of course, where your previous one ends. So if your previous one ends at 3, your next one starts at P4. And I'll say it's probably meaningful to end at P7, and the best line will be something like this. And what will be the error that you're paying for this one? It's the sum of length of all these red segments, how fits do I. And similarly, the next one, I guess if I picked R correctly, will fit all these points, and I'll pay all these distances. And that's the reasonable answer that I'll get if I pick R properly. But only by eye I can decide, hey, this is the R that I want or not. So we assume that the user gave us a specific R, and we need to say, I want to have 3 runs. I want to have the second one starts, the first one always starts at P1. I want the second one to start at P4, and I want the third one to start at P8. That's a good partition that the algorithm should spit out. And for each such run of points, each such subset of points, here are the 3 lines that fit them best. And how do I know that that's the best clustering? Because I paid for 3 clusters. I paid 3 times R, plus all the error here, all the error here, all the error here. And in this example, it's probably better than any other clustering that I'll do. If I just break it into two clusters, two runs, no matter where I will break it, let's say I'll break it into three and everything else over here, then now I need to find one line that will fit all these points. We'll go maybe here, and then I need to pay tons of penalty. So I paid only 2 times R because there is only 2 clusters, but the sum of errors in this expression error suddenly is much larger. If I pick 4R, I don't see any benefits in this example. If I pick 4 runs, I don't see any benefits, but I need to pay 4 times R. Penalty R times 4, and I don't really decrease the error by much because my lines already almost fit these points. Try to stick with this point until next class. People question about this one or anything else? I hope to have your grades today.